Welcome to my channel, and in this video I will explain about the case directory of an OpenFOAM case. So basically we have three main directories in an OpenFOAM case directory, which are 0, constant, and system. So 0 directory includes the boundary conditions and initial conditions for our simulation. So in CFD we have to define the initial and boundary conditions, and like inlet velocity and pressure outlet, or we may have side walls as symmetries like that. So we have velocity, pressure, and probably turbulence turbulence boundary conditions, and probably point displacement boundary conditions, temperature boundary conditions, etc. Okay, and in the second directory, which is constant, it includes the physical and material properties of the simulation, like transport properties and turbulence properties and the dynamic mesh properties, etc. And another one I forgot to write is, it's very important, it's the mesh. The OpenFOAM mesh, it's included in this constant directory. Okay, and the third one is the system. So in this directory we have our simulation controls, like how much time step do we want to set, how many time steps, or how long do we want to run the simulation, or the type of the solvers, and etc. And even how we want to write the results in like X key or binary format. And we also have numerical schemes. We may choose first order and second order Gauss-based schemes for partial spatial discretization, and we may choose like Euler or Crank-Nicolson for temporal time domain, etc. And the third one is the block mesh and Snappy hex mesh functions, which it's for meshing. And we can also have like separate files for post processing, etc. I will explain in later videos. So let's go ahead and look inside the overview of such an OpenFOAM case directory. So this is my case directory, and we have 0, constant, and system. So in this 0 directory we have u, epsilon, etc., and pressure, velocity, and this point displacement is for the motion of the mesh. So to use the moving mesh we need to move the points, so this boundary condition defines it. Okay, for epsilon, k, and omegas are for turbulence boundary conditions. We can use both k epsilon base or k omega base turbulence models by setting like this. Okay, and in the constant directory we have this guy, the polymesh. It's a bit important because this is our mesh, and inside the polymesh we have these boundaries. We have the faces, neighbors, and the points. Okay, and basically this is the mesh, and this is the transport properties, where we can have like density, okay, mu, okay, sorry, it's rho, density, or kinematic viscosity, or maybe we can define dynamic viscosity. It depends on our solvers. Okay, and in this tri-surface directory, we have the STL file, which is the geometry input for meshing to be used by the Snappy hex mesh. And in the turbulence properties, we have we can set up and choose the turbulence scheme, like we can choose k epsilon or SST k omega, sparse LMRs, etc. Okay. And in the system, we have the block mesh ticked. As I mentioned before, and this system includes about the meshing, the numerical schemes, and the simulation controls. So block mesh tick is to create the block mesh, the background mesh for the simulation, and Snappy hex mesh is to create the unstructured mesh, as I explained in the previous videos. And okay, this control dict is the most important dictionary in an OpenFOAM case directory, because without a control dict it will not run. So this is like the minimum requirement for our case directory, and it will include like the solver names and the time steps and etc, input output IO etc. Okay, and the FV schemes, it's about the numerical schemes. We can use first order or second order schemes. You can use TBD schemes like that. And this guy, FV solution, is about the how we solve the Navier-Stokes equation actually. So in other words, we can set up the linear solvers, metric solvers, and we can set up the details of our solution algorithm. We can choose like simple algorithm or piso algorithm, and we can choose how many steps we want to use inside our simple algorithms, or do we want to use relaxation factors etc in this file. Okay, and the other files are not that important, but these are like useful. Okay. And we can have so many other types of files, like for multi-phase flows we can have set fields to initialize our fluid domain, liquid domain, and the gas domains etc, and we can have like topo sets to manipulate the mesh etc. So let's go ahead and look at the inside of such a directory. So this is the directory, and we have our zero, constant, and system. Just ignore these two guys. Okay, and zero file has this is the what looks like the velocity u, the boundary condition for the u, and I will not cover the details. I'll just show the outline. So, and this is for pressure, and we can have the dimensions, and we can see the amount, the value of our domains, and the types of the boundary conditions, zero gradients, or we can have fixed values. For velocity we can set the inlet value as a constant fixed value, and we can let the outlet as zero gradient. Okay, I will cover the rest later. Okay, this is like the K for our turbulence models, and K omega etc. Okay, So inside the constant, this is more interesting. Okay, so inside this transport properties, we can have the transport model, whether our fluid is Newtonian or non-Newtonian, and we can set the kinematic viscosity, or maybe even set the dynamic viscosity if we use different solvers. Okay. And for the turbulence properties, we can set up like whether we want to use turbulence model or not. So here I set laminar, and the turbulence model will not be used. So if I delete this and write areas, it means Reynolds average. It will use Rand solvers, Rand turbulence models, and we can define the name of our turbulence models. And this dynamic mesh is all about the motion of our mesh and of course our structure. I will not cover this because I will need a lot of time later. Okay. Then we have polymesh, and this is the mesh of our simulation, and we have the most important file for us is the boundary, because we can open it, and here look at our patches. We have sides, inlets and outlets, bottoms and top. So we can change the names of our boundaries here, and we can change the type of the boundaries from like patch to wall or symmetry, etc. And we need to adjust the boundary conditions from here according to this boundary. So for example, if you want to use wall for the sides boundaries, we type walls instead of symmetry, and we can choose we can change the boundary conditions one by one like this. Okay, to make it wall like this. Okay, so basically the double slashes, this double slash is to comment our text. It's OpenFOAM uses exactly the same synonym with to C++. So double slash means comments. Okay, and we need to end the every line with semicolon. Okay. Anyway, this boundary is the most important aspect of our mesh. For other files, this is just a very long list of our phases. So it's phase 1, and it has 4 nodes, 1 2 3 4, etc. like this. So we don't care much about this. Well, in the tri-surface, we have the STL file to be used by the Snappy hex mesh. Okay, then go ahead and look at inside the system. Okay, we have the block mesh dict, which I explained previously, and okay, here we go. Control dict. This is the control dict of our OpenFOAM case directory, and we can see the solver, which is pimple form, and we can see the start time and the stop time. So we can define from our simulation to be run from 0 to 200 seconds, and we can set up the time step, and we can set at what interval we want to write out the results, and we can even write like adjust whether we want to use fixed time step or not. If we put this adjust time step to no, it will run with constant time step. And for adjustable time step, we can set the current number, okay, and delta t. Well, okay, and this is the FE schemes. So this is the numerical schemes. Our simulation using OpenFOAM is transient simulation, so we will need to define the temporal discretization scheme where I use while. This is first order implicit and it's bounded and very stable, so I rather compromise the second order accuracy for stability. Okay, and for the gradient schemes, we can use Gauss linear with for the default, and for gradient we can use like limited function limited schemes, but I will make another video about this alone. Okay, and divergence schemes, we want to use second order accurate schemes for our velocity, and for the turbulence properties we first order is enough. Okay, we can have Laplacian schemes and interpolation schemes and asynchrot. Okay, and this one is a wall distance scheme, wall distance required for the SSTK omega turbulence modeling. For other turbulence models, we won't need this. Okay, and this is the FE solution file, and we can see the solvers, which means the linear solver, the metric solvers for each of our term. For pressure, we can use GAMG, and we can use smooth solvers for velocities, etc. Okay, and basically all you need to do is decide which one you want to use, and basically we need to copy this from somewhere and just adjust this file according to your imagination and your targets. Okay, and this is the inside of the pimple. We use the pimple form, so the algorithm is called pimple. It's a combination of simple and piso. Okay, if you're never heard of it. Okay, and we can set the number of the characters and the number of loops inside this algorithm, and we can set the residual controls, and we can set the relaxation factors, etc. Okay, and Snappy hex mesh ticked. I will not cover this because I already talked about it. And okay, this one is surface feature extract. So this is used to extract the surfaces features and the edges of our geometry. For example, if our geometry includes very sharp edges, we need to refine these edges, and this file is used to extract such edges. Okay, and generally you can use this one for most of the time, and all you need to do is change the name here to your STL file inside your constant trisurface directory. Okay, and the last one is the decompose predict. I didn't explain it about it. This is to be used for parallel processing, and we can have like in my on my computer I have 6 cores, so this is the number of maximum cores you want to use. So you can set to the number of your maximum core on your computer, and you can use different uh, partition methods to decompose the domain into several uh, sub domains and compute on each of your cores. So Scotch is useful for complex geometries, and it's like my go-to uh, algorithm for decomposing. So I use this one is just the setting is also simple. If we want to use something like hierarchy, we may need some other settings. Okay, so this is how it looks like inside an OpenFOAM case directory. Thank you very much.